Hey, what's up, everyone? So you know banach-tarski paradox, where you duplicate a ball via finite partition and Euclidean transformations, and you need to use the axiom of choice for that. Well, we're going to use the axiom of choice to solve the problem of induction, at least in some abstract way. So I'm not kidding around with this title here. So imagine you wake up one day in an alien universe. Maybe it looks kind of like this one. Maybe it is this one. I don't know why it would be an alien universe then, but whatever. Or maybe it's a universe with totally different physics or just totally different, right? Well, we're going to predict the future 100% correctly. There is a method for that. Alright, we're going to use functions to represent our theories. The real numbers are going to be our timeline, and this range is going to be the set of states that our universe can be in. For this example, I chose heads and tails. So for example, if I say f of pi equals heads, that means at time pi, the state of the universe is heads. We will pick big F to be the true theory. So this is going to be the function that at each point in time, it tells us the true state of the universe. This is the thing that we're trying to get as close to predicting as possible. Here is an example of a true theory where the set of states of the universe is heads and tails. This one tells us that if we look at a time t, and if t is a rational number, then the universe is in head state. If t is an irrational number, then the universe is in a tail state. So this one has a pretty nice pattern. But what if the true theory has not such a nice pattern to it? Or what if there is no pattern, rather, in a certain sense? For example, here I say that at time little t, the universe is in a head state if t is a busy beaver number, and the universe is in a tail state if t is not a busy beaver number. But the set of busy beaver numbers has no pattern in a computable sense. It is not a recursive set. There is no computer program that can, in general, for any number, tell you whether or not it's a busy beaver number. So this true theory is not computable in a sense. And in fact, our prediction method is so good that it's even going to work for theories that we cannot define in the language of set theory. So what is going to be this prediction method? Well, first of all, we're going to replace the set of heads and tails with just any state space. So big S is going to be the set of all possible states of our universe. And we're going to create a well-ordering of all the possible theories. So a theory in this case is going to be a function from the set of real numbers into the state space. Now again, the state space can have any number of elements in it that is 2 or more. It could be 2 elements, 3 elements, 4 elements. It could be infinitely many elements, countably infinitely many, uncountably infinitely many, uncountably infinitely many of any cardinality. Intuitively, you would think that the bigger the state space is, the harder it's going to be to guess or predict all of these states of the universe as time goes by, but it's actually not going to matter how big this set is, which is really strange to think about. So we're going to arrange all of the theories into a well-ordering. So basically think of it as like a linear line of theories from least to greatest, in which there is no infinite descending chain. So think of it this way. If you pick a theory, and then pick a lesser theory, and then a lesser theory, and then a lesser theory, your goal as the player is going to be to do this in a way that you can just keep going forever. So I pick this theory, and then a lesser theory, and a lesser theory, and a lesser theory, and I go on forever and ever and ever. But because there is no infinite descending chain, you're never going to be able to win this game. No matter how you try to play it, you're always going to get forced back to the first theory in a finite number of steps, no matter what you do. And by the way, this is going to be a really long list. It's going to have more elements in it than there are real numbers, at least. So this is a very long list of theories. So our prediction method, the way I would like to think about it is that this is going to be our favorite theory, and this is going to be our second favorite theory, and our third favorite theory, and so on. So when we make predictions, we're going to want to use our favorite theory possible. However, we are going to cross out theories on this list if they get anything in the past incorrect. So basically, our prediction method is we're at some point in time, we cross out all the theories that don't get all of the past correct, so we're looking at only the theories that get all of the past correct, and then we're just going to pick our favorite theory that does get all of the past correct. And that theory is the theory that we're going to be using to predict the present and all of the future, at least until it gets something in the past wrong, and then we're going to switch to a new favorite theory that gets all of the past correct and use that one to predict until it gets something in the past wrong, and then we'll switch until it gets something wrong, and then we'll switch until it gets something wrong, and we'll just keep on going like that. That's going to be our prediction method. Alright, I'm going to write big F sub x just to represent our favorite theory at time x. That's going to be the first theory in line that gets all of the past right at time x. So our prediction method is going to be wrong sometimes. It'll be right 100% of the time, don't get me wrong, but it will be wrong sometimes. So I'll write WF to represent the set of all times that we're wrong at with our prediction method. So that means that at time x, my favorite theory tells me that the universe is in some state at time x that is not actually the actual state that the universe is going to be in at time x. What I'm going to want to show is that if I'm wrong at time x and time y, and x is less than y, then fx is going to be less than fy. In other words, if I'm wrong at time x and I'm wrong at time y, and x comes before y, then the theory that I use to predict what the state is at time x is going to come before the theory that I use to predict what the state is at time y. So my ordering at the ordering of my wrongness forces the ordering of my theories. Sorry, the light is blinking. How can we prove this? Well, first of all, sorry, I have to turn off the light. I cannot take it anymore. So fx is going to be less than fy. That's what we're trying to prove. So at time x, we use fx to predict what happens at time x, and we use fy to predict what happens at time y. So the first thing I would point out is that fx has to be less than or equal to fy, and why is that? Well, fx gets everything right before time x. Fy also gets everything right before time x. But remember, we said that the definition of big F sub x is that it is the first theory in line that gets everything right before time x. And since Fy also gets everything right before time x, it must be that either Fy is literally equal to Fx or that Fy comes later in line. But they can't be literally equal to each other because Fx gets predicts incorrectly at time x, right? It disagrees with the actual state at time x. But Fy has to get all of the past right, meaning it gets what happens at time x correct, which means Fy of x actually gives the actual state at time x. So when you combine these two, you get that Fx is less than Fy. And what we can do with all of this is we can show that the set of all points in time at which we predict incorrectly, that this subset has to be strictly well ordered. And the way we can do that is, well, we just showed this. So assume that this set was not well ordered, right? Assume, for instance, that there was an infinite descending chain of times at which we're wrong at. In other words, it's not a well-ordered set. Well, that would imply that there's an infinite descending chain of theories, right? Because x less than y implies fx less than fy. So x1 greater than x2 implies fx1 greater than fx2. x2 greater than x3 implies fx2 greater than fx3, and so on. So if we did have an infinite descending chain, then we would have an infinite descending chain of theories. However, we supposed that there was no infinite descending chain of theories. We chose an ordering on the theories that was a well-ordering. So this can never happen, which means that this can never happen, right? Taking the contrapositive of this means not this implies not this. And what that means is that WF is, it's a well-ordered subset. Now that we know that WF is a well-ordered subset of the real numbers, we're going to prove some consequences of that. So the first thing we're going to prove is that if you have a well-ordered subset of the real numbers, then it is a countable subset. So I want to show that any well-ordered subset of the real numbers is countable. So here, all these notches are going to be my elements of WF, and it's going to have a first element because it is a well-ordered subset, and each element is going to have an immediate next element in line. So this element has an immediate next element, this element has an immediate next element, this element has an immediate next element, and what I'll do is say between this element and its immediate next element, I'll choose some rational number between them. Between this element and its immediate next element, I'll choose some rational number between them. And I'll do that for all the elements. If there is a largest element, I'll just choose a rational number immediately after it. If there is no largest element, then I don't have to do that. But that part's not really going to matter. Because what I've done here is I've shown that for each element, there is a unique rational number associated to it. So there can only be as many elements as there are rational numbers, right? Like I can't have more elements than rational numbers, and the rational numbers are countable, therefore WF has to be countable. And what that means is that as we're predicting at an uncountable infinity of different points in time, but our set of times where we could be wrong has to be countable. So the infinity of our wrongness has to be less than the infinity of our correctness, to put it one way. It's also going to be the case that any well-ordered subset of the real numbers has to be nowhere dense. What that means, basically, without getting technical, is that there's never going to be an interval of the real numbers where the points at which we're wrong are going to sort of crowd in that interval. In other words, if you take all the limit points of the set WF, that it would fill in an interval. I'm not going to go over it too much, so don't worry about it too much. I'll just kind of go over the proof real quick. So we'll show that if WF is not nowhere dense, then it's not well ordered. So let's assume that WF is not nowhere dense. In other words, WF is somewhere dense. That means somewhere there's going to be an interval filled with points of WF such that if we take all the points of WF combined with all the limit points of WF, it will actually fill in that interval. And what we want to show is that this is going to force WF to have an infinite descending chain. And I'm just using WF as just any set, basically. So say I take, say this is like a width of, say, 1, just for instance, then I can take an interval of width 1/2. It's filled with limit points, which means somewhere in there, there's going to have to be a point of WF, and I can choose that point. And then within a width of 1/4, it's going to be filled with limit points of WF, which means somewhere in there, there's going to be a point of WF. I'll pick that point, and then a width of 1/8, I'll find a point of WF, and then a width of 1/16, I'll find a point of WF. And I continue that infinitely many times, which means I found an infinite descending chain of points of WF now I can just take the contrapositive. So if WF is not nowhere dense, that means it's not well ordered, which means if WF is well ordered, that means it is nowhere dense. In other words, the points in time at which we'll be wrong will be a nowhere dense subset of the real number line, which is nice because it means you're never going to be wrong like a whole bunch of times in a row, in a sense. It's kind of hard to explain, but yeah, that's kind of what it means. And I'm going to want to prove that any countable subset of real numbers is a null set with respect to the Lebesgue measure, which basically means that if you have a countable subset of the real number line, that is going to be, it's going to have a measure, it's going to have a length of 0, right? That's what it means. Every countable subset is going to have a length of 0, where length is characterized by the Lebesgue measure. So I'm not going to go through all the technical stuff about this, but basically the idea is that WF is a well-ordered subset of the real number line. Well, it's a countable subset of the real number line. So we can pick the first point number 1, we can pick point number 2, we can pick point number 3, and so on, right? We can create a sequence of all the points of WF. So here's point 1, point 2, point 3, going on forever in a sequence. And then if I choose, say, any positive real number epsilon, say I pick epsilon to be 1, well, I could find an interval around x1 that is of width, that's of length 1/2. I could find an interval around x2 that's of length 1/4. I could find an interval of around x3 that's of length 1/8, and so on. And when I add up all of these lengths together, 1/2 plus 1/4 plus 1/8, they're all going to add up to 1, which means that I have covered WF with a total length of 1, or actually it could even be less than 1 because maybe some of these are overlapping, but that's fine if they're overlapping. That only helps my helps my argument. That doesn't make things more difficult for me. So I have covered WF with a length of 1 or less. But what if I picked a different real number? What if I picked a real number of like 1 over a googolplex? Well, then I could choose this interval to have width 1 over 2 googolplex, and this to be 1 over 4 googolplex, and this to be 1 over 8 googolplex. And when I add all of those up, I will just get 1 over googolplex. Well, now I've covered my set with a total length of just 1 over googolplex or less. And I can do this for any real number epsilon. So if you argued like, oh, well, I think 1 over Graham's number, that the length, the measure of WF is at least 1 over Graham's number, well, I could just pick 1 over Graham's number, or I don't know, 1 over 10 times Graham's number, and then go through these steps to find a covering of WF that's actually even less length than 1 over Graham's number, which means that the length of the set must be 0 in that case. So what we have shown now is that our set WF of all points in time at which our prediction method will get things wrong is a strictly well-ordered subset of the real numbers, a countable subset of the real numbers, a nowhere dense subset of the real numbers, and it is a subset of the real numbers with Lebesgue measure 0. Sorry again that the video is not what it was supposed to be. I am really struggling. So let me just explain. Let me explain what I think is going on here, right? So at a point in time, say we're using F0, and then as soon as F0 stops working, we jump to the next thing in a discrete jump, right? We're not like smoothly scrolling through these theories. As soon as we get something wrong, immediately at times after that, we jump to the next theory. And then as soon as that one gets something wrong, we jump to the next theory. And as soon as that gets something wrong, we jump to the next theory. And we'll make a big jump if we have to, but that's the way we move through the theories as we're moving through the times at which we're wrong. And since we're moving through the theories in a well-ordered fashion, we have to be moving through the points at which we're wrong about things in a well-ordered fashion. And this well-ordered fashion of the points in time at which we're wrong forces the points at time in which we're wrong to be only a countable subset of the real numbers. Now, so it's even better than what I described in this video, because I just talked about that we would predict the present state of the universe correctly 100% of the time. But actually, it's not only that, but you'll also predict the near future correctly 100% of the time. And not only that, but I assumed that, that at each point in time you use a theory that gets all of the past correctly. But what if you don't, what if you don't know all of the past? Well, it turns out, as long as at each point in time you know the arbitrarily recent past, that's good enough for the method to work. So maybe like your memory is getting worse over time. So at this point of the time, you remember the last second, but as time goes on, you remember less and less and less of the past, and you use the prediction method. Well, it's still gonna work. It's still gonna work. So that's really cool, and that's just one example too. You can actually come up with more wild examples than even that. And yeah, so if you were, unfortunately, you do have to be some kind of like uncountable infinity wizard to use this method. You have to be able to verify like instantaneously when you're right or wrong about a prediction. You have to memorize, an uncountable number of like recent events and what those states they were in, right? Or recent states of the universe. So like, you can't use this in real life. You can't even get close. This is like some like ridiculous infinity magic that we're dealing with here. But at the same time, to the extent that you believe in such infinity magic, it forces you to accept this really bizarre conclusion that I find way more counterintuitive than banach-tarski, because I don't know, duplicating a sphere, like, sure, I guess it kind of makes sense to me. And I guess this one kind of makes sense to me too, because I've looked at it, because I've studied it some. But it doesn't make sense to me in the sense that, like, it is just so weird. Like, the idea that you can be in a universe, you don't know anything about this universe, you don't know how it works. It might not even have a way that it works. It might just be that, some deity flipped a coin a bunch of times and used those random coin flips to determine the future states of the universe. And somehow you're predicting all of those coin flips they got. And you're just predicting it by doing this weird infinity magic. So, like, I think that's really awesome. I think that's really interesting. I think it's interesting philosophically. I think it's interesting mathematically. And there's other things, too. Like, instead of a real number line, say it was, like, some really long, like, ordinal number. And like a really long ordinal number that you flip around backwards, and you were like moving through time along that flipped around ordinal number, and you were looking at the past, and you use like this method, you would actually be wrong only a finite number of times in that case if you use this method, which is super awesome because the ordinal number might have way more notches in it than there are on the real number line. So even though there's even more predictions to be made, like a really large infinity of predictions to be made at different points in time, like a really large infinity of different points in time, you can not only be wrong only a countable number of times, you can be wrong only a finite, you'll only be wrong a finite number of times in that case. So something about that added structure makes the prediction method even better in that case, which, I'm not going through the proof of that, but the proof is pretty simple. You can actually learn all about this. I will definitely link the references. You can learn all about this. I would say the background you would need would just be like to have taken one like theory class in math, one proofs class in math, and ideally like one additional like proofs-based math class, just to have a little bit more experience under the belt. But you could do it after just 1, or you could do it with 0 if you just like, you know, you could do it with 0. I don't know, that might be kind of... Okay, I'm starting to ramble now. Delete the last things I said. I'm actually not sure. I'd have to think about it, but yeah, I'll link the references. If you have any questions or comments, I would love to hear them. And yeah, thank you for your patience with the lighting and the rambling and all of this stuff. Yeah, have a good one. Take care.